Okay, I believe we're back. So now I will be talking about relativity, and so I know that I have mentioned a little bit about this before in the quantum mechanics episode. So what I like to say about relativity is that the concept itself is harder to grasp than the math and the application. Now, in some terms of relativity, it's a little bit harder to grasp the math when it gets into the more electromagnetism and gravitational time dilation and whatnot. But what I'm planning to talk about, which is the relativistic effects of moving at speeds close to the speed of light. I want to point out that the math itself is not too difficult to grasp, but I will do my best to explain the concept as well. So, with relativity, so I'll just explain the word relativity in general. So, let's say that you have someone moving this way. And so let's claim this is a vector. So let's say let's just make this a picture. So we'll put a car here. That is a terrible car, but we're living with it. It's a truck. Okay. So there's a car on the road here, and he's moving this way. And let's say there's an on-ramp to the highway, and I'm going to get rid of that one. So there's an on-ramp to the highway, and so I'm just going to add some details in here so you can see this is a road, and we got the on-ramp. So you see what I'm saying. So then we have another car, and let's make this one blue. It's just going to be a big truck. So we got wheels and a front. So it's kind of like a dump truck or whatever. Okay, so we have this car and he's going this way. So then they have their own speeds relative to the ground, but in terms of relativity between each other, so let's plot out the vectors. So we have the first vector, and then if we add the second vector, actually it's so in terms of normal Newtonian relativity, or classical relativity, you would have the velocity of the first car is equal to the velocity of the second car plus the velocity, the relative velocity. So that's the velocity of the first car with respect to the second car. So what this means vectorially is if we have this vector, then this vector is equal to the other car's velocity plus the relative speed. Actually, I'm going to do this in a different color so you can see it. The relative speed and the relative velocity of the first car, this car, with respect to the truck here. So this basically means that the first car is moving in this direction, with this relative velocity with respect to the other cars. So if you were videotaping the car from the truck, this is the direction you would see it in, and that's how your mind would perceive it. But in terms with the ground, the two cars are both heading in different directions from the relative directions of the cars. So the first car would see the truck moving in this direction. So for the first car, the truck is actually moving backwards and slightly to the left, or slightly up, which you can see that this portion of the vector is smaller than the car's portion. So you get this vertical portion, but then there is a subtraction of the the rest of this vector, and that's why we see the relative velocity of the truck being to the left somewhat in with respect to the first car. So that's regular relativity, and so that's what people will. That's not necessarily what people will normally mean when they say relativity, because I feel like there's more of a popularity with the special and general relativity, the theories by Einstein and his colleagues and others that followed him. So I'm gonna clear the page here. So what happens is that when you get closer and closer to the speed of light, things start to get a little weird, because basically the speed of light is inachievable. It's infinity in terms of velocity. The only thing that goes the speed of light are electromagnetic waves, so like light and radio waves and whatnot. So and that is what we base the maximum speed on. So when what causes something to not be able to achieve the speed of light is the relativistic effects when that object gets close to the speed of light. So if you have something going half the speed of light, so let's say 1/2 times c, which is the normal symbol for the speed of light. And for those of you that don't know, the speed of light is around approximately 3 times 10 to the 8th meters per second. And I believe that is about 180,000 miles per second. I wouldn't quote me exactly on that, but I just got distracted by the AI. Just did something a little strange to catch the ball, and that's fairly smart. Yeah, so this is the speed of light in terms of the metric system, and that's what most people will use in a physics class, although it is actually a little bit smaller than that. It's about I think I was reading 2.99994 something times 10 to the 8th. So it's fairly accurate when you're doing everyday math with the speed of light, and I'm not sure why you would be doing everyday math with the speed of light. But okay, so let's say an object, let's just make a baseball or something, is going half the speed of light. Now we'll ignore the fact that it would just tear itself to shreds on any drag it was receiving or explode, and I'm not even going to question how it accelerated to that speed. But let's say it's already going that speed. So it's going this way at half the speed of light. Now there's an equation, and actually I should explain what happens, or at least mention what happens when you get close to the speed of light. So the way that physics counters an acceleration towards the speed of light is that when an object gets closer and closer to the speed of light, it shrinks, and it also gets more massive. So it sort of gains mass in a sense. I know in most physics situations it's sort of taboo to gain mass, but this is something to do with the E equals mc squared situation. So it's not necessarily creating anything, it's just sort of trading stuff out. So what happens is it allows it to remove the extra energy that it's getting by becoming more massive. But so it becomes more massive, it shortens in the direction of travel. So if the ball is going this way, then it would become like a disc almost. It would start to shrink in that direction specifically. And then also time is dilated, and that's a strange concept for people to grasp. But basically, for the ball that's going fast compared to a bystander which is not moving in relative to the ball, or is moving at a fairly slow speed in terms of the speed of light, the ball would experience a stretched out time compared to the bystander. So for the bystander, the ball would be traveling for a much longer time than the bystander would be watching it. So let's say this ball traveled from point A to point B, and so it goes all the way from point A to point B at half the speed of light. Then the innocent bystander standing out here with a stopwatch would time the ball to get from point A to point B, and he would say that the ball took blah blah seconds to reach point B after being fired from point A at half the speed of light. But if there was a stopwatch on the ball, and we'll ignore the fact that the watch would probably break in the process, the stopwatch on the ball would read a shorter time from in getting from point A to point B than the stopwatch that was not moving. And this is due to the time dilation at relativistic speeds. So all of these effects that I've mentioned are computed based off of one equation for a coefficient called gamma. And this equation is that gamma is equal to the square root of 1 over 1, I believe it's minus v squared over c squared. And I'm pretty sure it's minus. So this v is the velocity that it's going, and this c is the speed of light. So you can see we have a c in our velocity, and so if we plug that in, we get a c squared and then 1/4 c squared. And so when you divide that by c squared, you just get 1/4. So this would be 1 minus 1/4. And then 1 minus 1/4 is 3/4, which is 0.75. And so we'll keep it 3/4 for simplicity's sake. And when you put that under 1, then you know how division works with fractions. So 1 over 3 over 4 is basically 4 over 3. And so then it's the square root, so it's the square root of both of these. And the square root of 4/3, I'll just do that real quick to give you an answer. Square root of 4 divided by 3 is So for our circumstance with the 1/2 the speed of light, the gamma coefficient would be equal to 1.15, and there's some terms after this, but this is the overall number. So this 1.15 can be used to find the first the shortening of the object. So if the diameter was originally, let's say, I don't know what's the diameter of a normal baseball, maybe 8 centimeters. So if the diameter was originally 8 centimeters, and then you can multiply. You can actually, so you divide that length by the gamma, which is 1.15, and at this speed, 1.15, the actual length of the ball, according to a person that is not moving, would be about 6.96 centimeters. So you can see that when you get to even half the speed of light, it is a noticeable difference in length. And so, although in terms of practicality you wouldn't be able to even comprehend that difference in length based off of how fast the ball was flying past you, this length is noticeable. But one thing that you would be able to notice is that is the time dilation. So what happens is that the time that the ball actually takes we'll call T prime, is equal to the time that the ball experiences multiplied by this gamma factor. So let's say, I'm not sure how big of a gap we'll need, but we'll say that the ball would take 20 seconds to get from point A to point B. So if the ball is going at the speed of light and it takes 20 seconds, then obviously that needs to be 20 light seconds away. But that's what we measure from a non-moving reference frame. And so then the ball would experience a time of, so if we had 20 seconds and we're the one measuring it, so then we have to divide it by gamma, 1.15. The ball would only record a 17.4 second time. So then that means that this could become problematic if we ever had any space races with extremely fast spaceships. There would be some confusion with how fast the one ship crossed the line compared to the timer. Now, I'm sure we will deal with that problem when we get to it, if we ever get to it. But you can see that the relativistic effects, when you get even to the magnitude of the speed of light, they become evident in the numbers that come up. So where do we use this in actual everyday life? If you've ever used well, actually, this is a different aspect of relativity, but GPS actually has to be calibrated for the relativistic effects, because as well as moving fast, there is also relativistic effects in a gravitational field. But when you have a satellite that is far away from the Earth, then it's experiencing a different gravitational field than something that would be on the Earth's surface. So this is not that massive of gravitational field in terms of what could possibly be used for a gravitational meter stick. We could say the sun, for that matter. I don't know if you've ever seen the diagrams of how many Earths can fit in the sun, but it is a lot. I'll keep the story short. So the Earth is not that big in terms of what even our solar system has to offer, but the effects of the gravitational time dilation are evident, especially over time. So when a GPS is running for a long period of time, when a GPS company has been around for a while, then odds are that at some point in time, it's somewhat like how we have to every once in a while shift the calendar to so it's why we have leap years. Relativity is not why we have leap years, but I'm trying to make an analogy. So if the Earth actually moves around the sun in about 365.24 or something days. So this is fairly close to 365.25, which means that if we just shift the calendar every 4 years, then the Earth stays fairly lined up, but it's not perfect. And so the actual, I believe that the method we use now is that every 4 years we shift the calendar, but if the year is also divisible by 100, then we don't shift the calendar. But then if the year is divisible by 400, then we do shift the calendar. So then the amount of time that the amount of days it would take for the calendar to shift one whole day without us accounting for it would be a very, very long time that will eventually become a problem, assuming that the human race continues to keep kicking it. But for now, it is not a problem. But in terms of the relativistic effects on GPS, what the point I'm trying to get across is that even a small change in the amount of time that occurs can add up over a long period of time. Now, I know I'm saying time a lot in the same sentence, and I hope I'm getting the point across, but that is the idea. So I don't have much more I want to say on this topic. Obviously, it's a little bit out of my league to try and explain more in depth the occurrence at relativistic speeds and gravitational fields. But I hope that I have at least given you some insight into the math behind relativity and the different effects that happen at very fast speeds. So I will move into my final segment, which is the segment I've been doing on my Saturday streams. So that is the segment where I pick random words and draw them. So I will play a short ad and transition into that. I will be right back.